Hello everyone, welcome back to our YouTube channel, Becoming a ROS Developer. I am Desire, and today we've got Soroush, who has just completed the course Linux Basics for Robotics, and he'll be giving us a presentation on that. So first of all, we would like him to begin by showing us a demonstration on the real robot, and then after that we can get into the details about his project, how he did it, and we'll also be asking him questions as we go. So, without any further ado, let me hand over the platform to him so he can begin his presentation. Alright, whenever you're ready, Soroush.
Yes. Okay.
Alright, so you can be explaining what you'll be doing or what the robot is doing.
Yes. So here I have my code. Can here.
It's fine, I think we can open the scripts after. It's just we want to know what is happening in each terminal. So
In this one, we have the distance that the robot just had from the beginning of the execution of the code. Then we have the odometry position, the odometry orientations, and the IMU, angular velocity, and linear accelerations. Then based on, and this one is like current robot direction is like east south. And then here we have the all the parameters that we are setting to just move the robot and just also avoid to collapse with the obstacles. So here, for example, we have the left distance, front left, front distance, front right, and the right distance. And also our threshold is 0.3. So for decision making, if for example front or front right and front left is blocked, so it's going to start to rotate. Also, if for example front is for example above the 0.3, above our threshold, and also all other parameters is also above the threshold, I just make the decision to just go forward instead of for example go on the other direction. But if front is blocked and front right and front left is not blocked, so I will choose which one is bigger and then go in that direction.
okay.
Is the same for others, so it's kind of decide which direction is the best for him.
Okay. Alright, alright, alright.
And also for rotation, I put like 0.5 for the angular velocity, and also it's gonna kind of rotate by 0.3 the seconds. So if the multiplication is like gives us then like 45 degrees each time it's going to rotate.
Okay. Alright, alright.
And then yeah.
So
And
right
so
now,
here for example it's
yes, go ahead. Yes, that's the part I wanted to know.
yeah. Yeah, so here it was a corner, and so it just got, for example, the front here. You can see it was blocked, and then it's going front left was blocked, so it's kind of rotate a little bit because it was on this side, and then rotate right positions to just get forward and have more distance to just follow.
Okay.
Here, for example, here we have that I think the front right was at some point, yeah, here. So it was a threshold, but at this point, front right, once it goes close to these obstacles, block, so it starts to rotate a little bit counterclockwise to just find a better path and then follow forward. And here again, here, for example, we have the right blocked. That's why it's kind of rotate a little bit, turning left to just avoid these obstacles.
Okay, I see.
And here, for example, here again, front left is blocked, so it's in turning right and to just go forward.
Right. So
You can see,
I see that right there as a result of the stationary obstacle, right? So the mini wall that we have
yes,
got there on the right side of the
yeah,
robot,
exactly.
right? If we are considering where it's going to be the front, right?
Yes.
it has made a couple of turns and maneuvers to try to avoid the obstacles. So the first time I think it rotated very close to the wall, so it rotated counter clockwise, and then it went to
Yeah.
the stationary obstacle there and rotated. This time it was counterclockwise, right? And then it did that
Yeah.
again. And I think you can see that there are some places where it considers to have obstacles on either the front right or front left, even though the obstacles are
Mhm.
not too close enough. Can you tell me what would you change to make it realize that a lot sooner, or to not make as many stops and turns as it did there?
Oh, okay. So you meant, for example, at some point that there is front right and front left.
Mm-hmm. Because why I'm
Mm.
saying this is clearly it was stopping because it was considering that the front left had something to it, and then the front right was clear, but because front left was not clear enough, it had to make an extra rotation, right?
Yes, because front right, the threshold, the value of front right is bigger than front left. So
Ah,
it's rather to turn on that direction and find more spaces to go forward, to
okay,
just reduce the time, the whole time of lapse
okay.
that it just passed.
All right. So what would happen if you increase the number of sectors that it has to take into consideration?
What do you mean by the number of sectors?
Oh, so okay. At the moment, right, the area around the robot is being split into how many? It's you're taking into consideration 8 laser scan ranges. Is that right?
Yes.
What would
Yeah.
happen if you used, let's say, for example, 16?
Oh, okay. So then we have, for example, 16 conditions.
Mm,
And with those 16 conditions, we can just calculate. And I think maybe the best like navigation algorithm would be which directions, for example, which of those 16 has the highest value, and then just rotate on that directions and go forward on that directions.
mm,
And if, for example, there are not difference a lot between the direction, just for example, prefer to go forward.
mm,
Here also I calculated, for example, in my code that if, for example, the front, I think at some point, for example, front right is like 0.302. So it's very near to my threshold.
mm-hmm,
So the time to move, if I calculate the time to move here,
mm,
it's like 0.302 minus zero point 0.3 and divided by the distance. So it's very little time and sometimes it's very short. So on that conditions, I put a if condition. If that one is too small value, just consider that the time to move to 0.05.
mm. Okay.
So
So,
if we have
all right. So,
more laser scanners, it's easier to just calculate those values and just prefer which direction has the highest value and go in that direction. But
uh huh.
also we should care about that it just not got is stuck because I think if it was a clear pass and it sees that the whole pass is not clear and it's going to go back. So we should just avoid that and have like some memory to not going back. And
Okay.
just remember the last task was, for example, forward.
Yes.
So avoid to go backward. Because here also with some speeds at the corners, I figure out that if we set the values of this one, for example, the angular velocity,
Mm-hmm.
it was if we set it high, it's just kind of going like around itself and just twisting all over and that
Mm.
stuff.
Mm-hmm. Okay. So, okay. So you're saying that increasing the number of laser scan data indexes it has to take into consideration might make it a lot more unpredictable because it will consider all those to be blocked in cases where
So no,
they're too close
no, I
or
think we have more flexibility to write in a way that just finds the better path and that
okay,
can move forwards much more.
okay,
But
yeah,
it
yeah, yeah.
definitely would be like complex than this algorithm because with this we follow just like very, I think, basic navigations.
Yeah, 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 true. Yeah, I understand why you say that it will make better decisions because you are taking more samples, right? So you would actually know
Yes.
where the things are. So yeah, that's quite good. I had another question, but you can keep going. If I remember it, I'll ask you now.
Okay. Yeah. So now I can go for my codes to explain that one.
Yeah. Oh, okay. By the way, I just remembered. Okay, the question that I wanted to ask you is,
Oh, okay.
with regards to the threshold value, right? So, are you taking zero point 0.3 for every laser index that your robot is receiving? So, like if the robot is moving forward, right? There's front left, there's front, and then there's front right.
Yes.
So, are you
Yes.
checking that do all of those three satisfy the condition of being above zero point 0.3 for it to move, or it's just one or two? How are you
No,
doing it?
no, I consider all of them because
Okay.
if you consider just the forward of point three,
Yes.
or the front right, for example, at some points it's going like this way, and then if going to because it can be close to here, and if
Uh-huh.
it rotates, I don't know the dimension of this robot, but it
Yes.
seems that it may just collide with the wall.
Okay. Okay. That's why
So I
you.
think it's better to just have all these sensors.
Yeah. Very nice. I did see it avoid a near miss very well, and that made me think, what did you do to make it do that? That's why I was asking, how many of those indexes are you making sure that they are either above or below a certain threshold for you to for the robot to make the decision. So that was very good. That was very good. Yes. Um. All
Yeah.
right.
And also I set, for example, 10 minutes for the runtime.
Uh-huh.
And, and I think in 10 minutes it just goes.
Or it will just stop. Okay.
And I don't know what is the optimal time.
No,
Yeah,
I
yeah,
think this
because
is.
I set that, for example, that the robot just doesn't like go around all the time. I
Uh,
just set a limit of 10 minutes.
no, it's fine. I think it's fine. We have seen it done. We have seen doing like the obstacle avoidance that we want. So that is really good. Let's get into the scripts themselves.
Okay, sure. Mhm. So here I have the robot statistics that just have all the odometry positions,
Mm-hmm.
orientations, and the IMU, angular velocity, and the linear acceleration.
Mm-hmm.
And then we use those to have like obstacles avoider, our bash script. So we set the all the velocity like to zero
Mm-hmm.
to make sure that there is no previous movements from like previous codes or something from the system. So we set the threshold for zero point 0.3 and the linear speed of zero point 0.1 and the angular speed of zero point 0.5. And also the turning time is like zero point 0.3. I calculate zero point 0.3 by just like uh, try different things to see which combination of these two just give us the like 45 degrees because this one like this is like 0.15 radian.
Okay,
Then
so
we have
45
like
degrees.
backup.
45 degrees was your prime value. That's the angular distance that you thought will give you proper obstacle clearance.
Yes.
Okay, all right.
Because if it was less than that, it's just rotating not a lot. So we should, for example, start to turn multiple times. But with
Yeah.
this one, if there's obstacles, can just turn.
Okay, okay, I see.
Yeah, and so we have like backup time and like maximum stock count. If, for example, at some point it's just stuck, then we're going to after four times it's going to like backward.
Mm-hmm. Okay.
And so for example, just remember what is the last term. So here also we validate the sensors. Uh, and here is we have that left, front, right, and the right values that we're just reporting here. And then we have three statements uh, that is front left blocked or front blocked and front right blocked, and the combination of these. So we calculate the time to move, front minus the threshold, and then divided by linear speeds and some value for the delay and latency. And
Mm.
if here is that I mentioned that if the valid time to move is so small, like or less than 0.05, we just set the time to move like 0.05. And
Okay,
if
so you
it is
put a fixed
very
value for
large,
that.
yeah.
Okay.
And here is also like a conservative condition that if the time to move is a lot, because we don't know, maybe something happened in the middle, I set the just time to move like 0.5.
Okay, so you're trying to put a safety net for it.
Yeah, because actually this one is not necessary, but it's like another to just avoid anything in the middle. Because
Yeah,
maybe
I
in
completely
general
agree. Yes.
conditions, I think some things comes, for example, in the past here, because we have a static environment, it doesn't matter actually. We don't need this one.
Yeah,
But if,
yeah.
for example,
But
something
yeah,
in the middle comes,
I think I completely agree with your decision there. It is better safe. It is better to be safe than sorry, right? So yeah, that is a very interesting way of implementing that safety net. But yeah, I completely understand how it works. So well done. I like that bit.
Ye- yes, thank you. And also here we have the decisional logic that if just turned and if the front blocked, then just linear calculate the linear speed and some sleep time to go in that directions.
Mm-hmm.
Here is like it helps me to just avoid stuck at some point.
Mm.
And the
Can,
other condition is if yes,
can you
can
explain a
go
little
ahead.
bit more the logic of not getting stuck at one point, right? How do you avoid
Yeah.
that there?
I have it. This one is like just turn. If the robot just turned,
Yes.
and if the front is not blocked, it said that just turn and let's move forward. So I just set the command velocity of linear just go in that directions. If if we don't have this one, I figured that if we start the robot from some points that goes directly from here, like the forward of the front of the robot be in these directions, then it's just going to turn around a lot about itself.
Okay. All right. All
Also,
right.
we can control that one. Actually, we can control that one with the linear, the combination of linear speed, the angular speed, and the turning time.
Mm-hmm.
But I assume that maybe it's better to have another layer of getting stuck to just avoid any other
Yeah. It
like
is.
weird
It
conditions.
is good to have redundancy. So yes, I agree with you there. Yes.
Yeah, thank you. And so here, and here is the other conditions. Like if not, none of the front is not blocked. So just moving forward and then set the command velocity to the linear speed and the time to move.
Mm-hmm.
And then if front left is blocked and front right is blocked and if front is blocked and front right is blocked,
Mm-hmm.
just set that we have like we kind of stuck at that point. So just consider if that one is greater than the maximum state the count, just set the command velocity of minus zero point 0.1, just go back up, go back a little bit.
Mm-hmm.
And then that one is like a backup time, the amount of time that goes just backward.
Have you
And
encountered
also,
a case where this had to work? Like this had to execute actually.
yeah, sorry, can you repeat that again?
So during your testing procedure, right? Did this go back algorithm had to be executed at some point, and under what condition did it have to actually
Yeah,
go back?
actually, the condition that it goes here, and then I think from here, then goes here. If it goes to here from this point, if you can see my
Uh,
mouse,
yes,
right?
yes. So it would
Yeah,
have
if
both
this,
front left, and front right blocked.
yeah, and I think the only thing, because it's if for example here it's here, then it doesn't have enough space to just rotate.
Uh huh.
So it's better to just go backward and then just consider them again.
Okay, all right. Can you like move it with the joystick and put it there so that we see if it can get these things to do these things? Yeah.
Yes.
Or you can move it into the corner just beyond the threshold, right? So we see.
Yeah. Why it moves like slow?
Is your script still executing? No. Okay. No, it's not. Okay, it's fine. I think this is just maybe a latency thing, but yeah, it's fine.
Yeah.
right. I think that's good enough. So let's see.
Yeah.
Okay, I did realize there's something
I
there.
think I think here it's like I don't
Okay.
know. Because now all of them are
Upload.
front left is not blocked.
Mm.
The frontal left, I think, I don't know why it captures. I think it now here is that why we have like 8 LiDAR sensor if we have like 16
It would
this
notice,
amount.
right?
Yeah,
Yeah,
because
yeah.
now here you can see it wasn't the value was shouldn't be like 0.822.
Yeah, yeah. But it's all right. I think this is a very extreme case, right? It is an extreme scenario. So, oh, you have to stop it. Um,
I have stopped. Yes.
um, but I do like the way it gets around. So, I think on that note, we can say it's been a wonderful presentation. Thank you so much, Soroush.
Thank you
So,
so much.
so just hang on and we wrap it up. You okay?
Okay, thank you.
Alright everyone, this was Soroush's presentation and we'd like to congratulate him for a job well done and also for explaining very clearly what he did and why he had to implement these algorithms the way he did. So until further, I would like to encourage all those of you who would like to give an attempt to the courses that we offer certification on to do that. And then until then, I encourage